Hi, I'm Ryan Baker, and this is Big Day in Education. This week, in honor of American Thanksgiving, we're going to talk about something that I have cause to give thanks for all the time, which is visualization. In specific today, we'll talk about learning curves. So what is visualization? Visualization is displaying information in a meaningful fashion. According to Edward Tufte, who is just down the West Side Highway, visualization should do a few things. First of all, it should show the data. But more importantly than just showing the data, it should induce the viewer to think about what it means, to think about what the substance of the data is. It should avoid distorting what the data have to say. Tufte's book and a lot of things since then really illustrate the way that you can really distort the meaning of your data by the way you present it. And the goal is to not distort the data, but let the data give you its meaning. Make large data sets coherent. Actually, it turns out that the methods for visualization of very big data sets are not always the same as the methods for visualization of smaller ones, and we'll talk a little about this week. It should encourage the eye to compare different pieces of data to each other. It should allow the differences to kind of pop out visually and become meaningful. It should reveal the data at several levels and allow a person to get aggregate or more piece-by-piece views of the data. And finally, it should do all kinds of other stuff. Visualizations can be useful, can be good or bad on multiple dimensions, and this week we're going to talk about a bunch of visualizations and what they're good for. Visualization is a big area, and it's worthy of a course in its own right. Anyways, rather than discussing standard visualizations, which you can probably learn about from a variety of sources and you've probably already seen, I thought that in this lecture and in this week, I'd discuss a few visualizations that are particularly important in the domain of education. One of the most important visualizations in education is the learning curve, which we briefly discussed in week 4, but I'll go into more depth today. Let's start by discussing the classic learning curve. First of all, let's talk about its assumptions. First assumption, the student is practicing the same skill several times in approximately the same fashion. For example, completing a physics problem set, or rereading the same word in several stories, or learning to complete an assembly line procedure. One of the early uses of learning curves came from Crossman's work in looking at assembly line workers. Similar methods and considerations apply to situations where the student's recalling the same knowledge several times. It doesn't have to be a skill, it's kind of neutral to the type of knowledge component you have on hand. Another assumption, we have some way to measure student performance over time. Might be speed, might be accuracy. Could be other things like the amount of assistance the student needs to get the right answer. Here's a classic example of a learning curve. This comes from Corbett and Anderson 1995, which, sharp observers may note, is the exact same paper that had Bayesian knowledge tracing. In this system, they were looking at how students learned Lisp programming in the Lisp tutor, and they looked at how the error rate dropped at each opportunity to use a given skill. And you can see for this skill this nice, lovely little curve that kind of shows the student getting better over time, and it's fast at first and kind of slows down over time. Here's another example from Cognitive Tutor Geometry by Steve Ritter. And you can see in this case that it's how many problems the student completes for a given skill and how many times it takes them to solve it. And you can see that over time, again, you get this rapid decrease and then this slower decrease that kind of levels off over time. So you may note in these two graphs a certain characteristic pattern, which is sometimes called the power law of learning, which says that performance, both speed and accuracy, improve according to a power function, which is again going down rapidly at first and slowing over time. Now, I've got that big asterisk there because, in fact, the power law of learning may really be the exponential law of learning. It may really be an exponential function rather than a power function. And believe it or not, people have holy wars about that debate. And it's called the power law because speed and accuracy both follow a power curve, which is radical improvement at first, which slows over time towards an asymptote. And the asymptote is the point that you just never get better than. Passing the asymptote usually involves developing an entirely new strategy. For example, take the classic example of the Fosbury flop. I'm not actually going to embed the video here, but I encourage you to copy this out and go into YouTube and take a look. The Fosbury flop was a way that people were able to jump in a new way that made them able to jump higher than they ever had before. There's other asymptotes. For example, when you're learning long division, finding shortcuts that make division faster that allow you to just go faster than you did before. The power law of learning, outside of these passing the asymptote cases, has been shown to apply across a whole lot of domains, including simple cognitive psychology domains like pressing the correct button on stimulus, complex problem-solving domains like math and programming, and real-world domains like cigar making in factories. Now, You may note that you see these nice curves, but those graphs we saw earlier for Ritter and Corbett were not all that smooth. And in fact, real-world data is rarely perfectly smooth, unless you have hundreds or thousands or tens of thousands of students. Now, if you look back to that example from a minute ago, you'll see that actually there's a lot of cases where it's relatively far off the line, even fairly late in the process. For example, over at 80 problems, there's a case where it took 400 seconds. So how can we make inference from learning curves? Why are they useful? Why are they more than just kind of a cool little picture? Well, what you can do is you can do visual inspection of the curve form. So, for example, here's normal learning. You can see that the student kind of goes down rapidly at first and goes towards an asymptote later. Here's a case where there's no learning going on at all. It's just jumping all over the place, and you can see that the scale on the y-axis is pretty compressed. So it's taking like 19 to 21 seconds, and it's just not getting much better over time. This is probably somebody who's completely at the asymptote and has been there for a while. And the fact that it looks like jumping going around is just because you're only seeing the asymptotic part, so the y-axis is completely compressed. So what might this graph mean? What it probably means is that the students already learned the skill for the most part. Even though it's kind of jumping all over the place, if you look at that y-axis, you'll see that, for example, for time, 0 to 2.5 seconds is really fast. So whatever skill this is, the students probably got it. And similarly, if it's error rate, then the student's 0 to 2.5% wrong. Again, probably the students have learned the skill, and what we're seeing is just a compressed scale. How about this graph? What might this graph mean? What probably happened is take a look at where it kind of is going down, then it flattens out the asymptote. It looks like we're just in another case of the student learned, but then suddenly it jumps down again. What probably happened here is the student learned a new strategy and they broke through the asymptote, like the Fosbury flop or like learning a new strategy for division. How about this graph? What does this graph mean? What Corbett and Anderson argue is that this one represents two skills being treated as the same skill. You see it going down here, and then it shoots back up because it's actually a new skill, and then goes down from there. So we've got two skills, we think they're the same skill, so we get this kind of telltale pattern. And in fact, this kind of pattern actually is a well-known pattern that people use a lot to try to distinguish when they need to split two skills. So how do you use these learning curves? First of all, to understand how and whether a skill is being learned across students. A second use is to study and refine item skill mappings in educational software. Now, as discussed in week 4, the Pittsburgh Science of Learning Center Data Shop is a common tool for doing this. However, because of the noise in these kind of graphs, people don't use them very often to study individual students. They use them more often to study kind of whole curricula or whole skills. I'm Ryan Baker. This is Big Data Education, Visualization Week. Awesome to have you. Hope you're having a great day. See you next lecture.